Quantum mechanics is a core branch of modern physics, like a key attempting to unlock the mysterious gate to the microscopic world. It focuses on exploring how matter and energy behave at extremely tiny scales, on the level of atoms and even smaller, subatomic particles. In our daily lives we deal with the macroscopic world, but in this microscopic realm, everything seems to overturn the rules we take for granted. Born in the scientific revolution of the early 20th century, quantum mechanics instantly created waves of thought. It not only reshaped our basic understanding of the physical world, but directly challenged the classical concepts that had reigned since Newton for centuries. Many of its ideas, for example, that a particle can exist in multiple states at once, sound like science fiction, yet they have stood the test of rigorous experiments, leaving people astonished. The driving force behind the development of quantum mechanics was the need to solve puzzles that classical physics could not. Problems like blackbody radiation, once called the ultraviolet catastrophe, the photoelectric effect, which made people question whether light was a wave or a particle, and the mysterious lines in atomic spectra, all of these phenomena pushed classical theory to its limits and forced scientists onto a brand new path of exploration. The deeper scientists delved into the nature of light and matter, the clearer it became that this was not a neatly predictable world. They had opened a door to an unknown realm, a universe governed by probabilities, riddled with uncertainty, and filled with elusive particle behaviors. Here, particles are both waves and particles, their actions resemble dice throws, and outcomes are always tinged with ambiguity. These seemingly counterintuitive discoveries ultimately built the grand theoretical framework of modern physics, quantum mechanics. One of the most surprising and central ideas in quantum mechanics is the so-called wave-particle duality. In simple terms, microscopic particles such as electrons and photons can behave like obedient little balls zipping around, but they can also act like rippling waves that interfere and diffract. They are not confined to being just wave or just particle. Instead, how they appear depends on how you observe them. It is a kind of quantum magic bestowed by nature. To understand wave-particle duality, the most classic example is the famous double-slit experiment. In this setup, scientists send tiny particles like electrons toward a barrier with two narrow slits placed close together, like two fine lines on paper. As the particles pass through, they seem to face a choice: go left or go right. Yet in reality, things are far stranger than they seem. The astonishing part is that when both slits are open, the particles no longer form two simple spots on the screen behind, but instead create a series of bright and dark bands, an interference pattern, just like overlapping ripples on water. This shows that the particles did not simply choose one path or the other, but somehow took both paths at once and interfered like waves. It overturned our very definition of what a particle is. Even more baffling, once we add the act of observation to the experiment, trying to detect which slit the particle goes through, the interference pattern instantly disappears. The screen shows only two blurry spots, behaving like ordinary particles again. In other words, the mere act of looking disturbs the outcome. It's as if the particles know they're being watched, give up their wave identity, and behave like obedient little balls. This strange change, when observed, reveals a fundamental truth of the quantum world. Measurement itself alters the object being measured. Before observation, a particle is not in any definite state, but in a special condition called superposition. It exists across multiple possibilities at once. Only at the moment of measurement does it decide on a particular outcome. This idea radically challenges our conventional understanding of reality. Among the treasures of quantum mechanics, one concept is absolutely central: the wave function. You can think of it as a kind of map, not of cities and roads, but a mathematical map describing the distribution of possibilities for a quantum system state. The wave function is not just a mathematical tool, it is a bridge to the truth of the quantum world, the foundation of the entire theory. The wave function is usually written with the Greek letter psi. A simple symbol, yet it encodes all the secrets of a quantum system. It is like the most complex sentence in nature's language, containing every piece of information about where a particle might be and what state it might occupy. If you know how to interpret it, you can tell where a particle is likely to appear, not where it definitely is. So how do we get actual probabilities from the wave function? The answer is, square its amplitude. Just like squaring a current to calculate power, squaring psi gives us a probability density, a map showing how likely it is to find a particle at a given spot. This shift from certainty to probability is the unique perspective of quantum mechanics. This interpretation, linking the square of the wave function to probability, was proposed by German physicist Max Born. It completely changed how humans think about predicting the future. Before this, classical physics believed in determinism. If you knew all the starting conditions, you could calculate the future with certainty, like predicting where an apple would fall. But Born's interpretation told us, in the quantum world, such exact prediction is impossible. Everything reduces to chances. Unlike the rigid precision of classical physics, quantum mechanics introduced fundamental uncertainty, most famously expressed in Heisenberg's uncertainty principle. It tells us that certain quantities, like a particle's position and its momentum, its mass times velocity, cannot be precisely known at the same time. The more exactly you measure its position, the fuzzier its momentum becomes, and vice versa. This isn't because of imperfect instruments, it's because the universe itself forbids it. This principle carries profound meaning. It is not just a lab rule, but a philosophical shockwave. At the quantum level, the universe is not a perfect calculating machine, but more like a game of dice. It means our understanding of reality needs a complete upgrade. Perhaps the world is not predetermined step by step, but full of choice and possibility. As quantum mechanics evolved, it gave rise to a more specific branch, quantum theory of atoms. Especially when describing how electrons arrange themselves in atoms, scientists discovered that electron energies are not continuous but quantized, jumping like steps on a staircase. This phenomenon, called energy quantization, is key to understanding atomic structure and behavior. Before this, classical physics assumed electrons could orbit at any energy around the nucleus, with energies varying smoothly, like a car driving at any speed. But this implied that electrons would radiate away energy continuously and eventually spiral into the nucleus, making atoms unstable. Clearly, the real world doesn't work like that. Later, experiments showed that electrons are restricted to specific levels or shells. There are no in-between states. An electron is either on one level or another, never hovering between steps. It's like standing only on the rungs of a ladder, not in midair between them. More intriguingly, when an electron jumps between levels, it absorbs or emits a precise packet of energy in the form of light, a photon. These jumps are not random, but follow fixed rules. Because of this, each element produces its own unique spectral lines, like a light fingerprint that scientists can use to identify it. Energy quantization is not just a math trick, it is the foundation of quantum mechanics. It explains why atoms are stable and why elements behave so differently in chemistry. For example, hydrogen and oxygen can bond to form water, but helium almost never reacts with anything. These rules shape molecules, chemical reactions, and ultimately the complexity of life itself. The impact of quantum mechanics extends far beyond electrons inside atoms. Its reach now permeates materials science, chemistry, biology, information technology, and even cosmology. It is like an invisible current driving us ever further into the unknown. One of its most disruptive applications is quantum computing. This frontier technology is not a simple upgrade of today's computers, but a whole new paradigm based on quantum principles. It harnesses superposition and entanglement, letting information processing escape the binary 0 or 1 limitation and perform many calculations simultaneously, achieving speeds classical computers cannot match. All our current devices, from phones to laptops, operate using bits, which can only be 0 or 1, like a switch on or off. This system is reliable, but when tackling problems like climate modeling or simulating molecules for drug discovery, it quickly reaches its limits. Quantum computing introduces the qubit. Unlike bits, qubits can exist in a superposition of 0 and 1 simultaneously, like walking both left and right paths at the same time. This strange property allows quantum computers to process massive amounts of information in parallel, a leap in computational power. Thanks to this multi-threaded ability, quantum computers may revolutionize many fields, cracking advanced encryption, finding optimal solutions in business and logistics, or modeling molecular interactions in drug design. What once sounded like science fiction is steadily becoming reality. Today, scientists and engineers worldwide are racing to develop quantum algorithms and hardware, striving to turn theory into practical machines. Just as the steam engine sparked the Industrial Revolution, quantum computing could ignite a new technological revolution, reshaping information technology and transforming scientific research at its core. Beyond superposition, quantum mechanics also presents another mesmerizing phenomenon: quantum entanglement. This describes a mysterious link where two or more particles become in sync with each other at a deep level. No matter how far apart they are, even if one is on Earth and the other at the edge of the galaxy, the state of one instantly influences the other. Einstein himself was unsettled, calling it spooky action at a distance. That was exactly Einstein's objection. In his worldview, all physical effects should be local. One particle could only affect another through clear physical processes, never instantaneously. But entanglement shattered that notion. It seems to defy space and time, challenging the principles of locality and causality in classical physics. It remains one of the deepest tensions between quantum mechanics and relativity. Repeated experiments revealed something astonishing. Entangled particles display correlations that classical physics simply cannot explain. They are not just agreeing in advance and then parting ways, they remain fundamentally bound in a shared fate. Measuring one instantly determines the state of the other. This profound interconnection has been confirmed countless times, making it one of the strangest yet most undeniable phenomena in modern physics. Excitingly, this bizarre effect has found real-world use. In quantum communication, entanglement is used to create ultra-secure methods like quantum key distribution, QKD. It allows two parties to share encryption keys securely. If an eavesdropper tries to listen in, the system detects it immediately and shuts down. It's like having an unbreakable lock guaranteed by nature itself. Traditional cryptography relies on the difficulty of mathematical problems, like factoring large numbers. Quantum communication, by contrast, bases its security on physical laws. Since any measurement inevitably disturbs a quantum system, there is no way to secretly intercept without being noticed. In theory, quantum communication is virtually unhackable. As quantum mechanics has deepened, it has not only revolutionized labs but also shaken philosophy. The idea that particles are waves, or that measurement changes reality, forces us to ask, is reality truly independent, or is it partly created by observation? These questions spill far beyond physics, touching consciousness, existence, and knowledge itself, sparking debates across disciplines. Despite its flawless math and overwhelming experimental success, quantum mechanics still lacks a universally accepted interpretation. People disagree on why particles can exist in multiple states at once, or what measurement actually changes. Many models try to reconcile the bizarre quantum world with common sense, but none has fully convinced everyone. This is one of physics' most hotly debated and fascinating mysteries. One widely accepted view is the Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg. It says that before measurement, a particle exists in superposition, here and there, 0 and 1. When measured, it is forced to choose one outcome, collapsing the wave function into a definite state. This view works well in practice, but raises deep philosophical questions about whether reality depends on the observer. The Copenhagen interpretation emphasizes the role of the observer. Reality, it suggests, isn't a static thing waiting to be seen. It becomes definite because we observe it. This challenges our notion of objectivity and forces us to wonder, do humans only ever see the world we help create? It blurs the line between physics and philosophy. In contrast, in the 1950s, American physicist Hugh Everett proposed a bolder idea, the many worlds interpretation. He argued that the wave function never collapses. Instead, every possible outcome of a quantum measurement actually happens, each in its own parallel universe. So every coin toss splits reality into two, one where it lands heads, one where it lands tails. This theory upends the idea of a single reality. It suggests the universe is like an endlessly branching tree, with every possibility realized on a different branch. In one branch you are watching this video, in another you went for a walk, in yet another you became an astronaut. It sounds like science fiction, but within quantum mechanics, it has solid mathematical backing. While we cannot yet directly test the existence of these universes, it remains a compelling explanation. Undeniably, quantum mechanics sounds magical, but it is no fantasy. It is one of the most experimentally verified theories in modern science. From interference patterns to entanglement correlations, its predictions have been confirmed over and over. It is the most precise tool we have for understanding how matter and energy behave. And it doesn't just live in theory, it shapes daily life. The phone in your pocket works because of transistors, whose invention relied on quantum theory. MRI scanners in hospitals exploit quantum spin in magnetic fields. Lasers, solar panels, LEDs, all are gifts from the quantum world. In materials science, quantum mechanics opens the door to the future. Researchers are investigating exotic materials like topological insulators and superconductors, which behave in ways that defy conventional rules under extreme conditions. These could revolutionize quantum computing, energy transmission, and more. Quantum theory is laying the foundation for the next technological era. Of course, exploration always brings new mysteries. Just when we think we've mastered the quantum world, new questions appear. Can quantum mechanics be unified with general relativity? Could dark matter and dark energy be linked to quantum effects? These unanswered questions push us toward deeper understanding. One ultimate mission in physics is to find a theory of everything, uniting quantum mechanics with Einstein's general relativity. The former governs particles at the microscopic scale. The latter rules galaxies, black holes, and cosmic expansion. Yet the two do not mesh seamlessly, like incompatible operating systems. A true quantum theory of gravity is the holy grail of modern science. You can think of it this way. Quantum mechanics is the rule-maker of the micro-world, governing electrons, quarks, and photons. General relativity is the grand planner of the cosmos, controlling space, time, and gravity. Both work beautifully on their own, but in extreme conditions, like inside black holes or at the Big Bang, they clash. Bridging them is key to understanding the ultimate nature of the universe. To truly grasp the most extreme scenarios, the singularity inside a black hole, or the hot, dense birth of the cosmos, we need both quantum mechanics and relativity together. In these realms, gravity is overwhelming, but quantum effects are also intense. A unifying theory could reveal the deepest secrets of the universe, perhaps even answering the ultimate question: why does the universe exist at all? In summary, quantum mechanics is not just a set of equations, it is a revolution in thought. It overturned our view of the world, transforming the universe from a clockwork machine into a stage of possibilities and uncertainties. Each particle seems to whisper, "Don't judge me by old rules, I'm more complex than you think." This science has redefined our sense of reality. By introducing concepts like wave-particle duality, superposition, and entanglement, quantum mechanics reveals a universe ruled by probability and inherent uncertainty. What seems absurd to common sense is, in fact, the everyday reality of the micro-world. From the early mathematical descriptions of electrons to today's breakthroughs in quantum computing, communication, and cryptography, quantum mechanics has gone beyond academia to become a powerful engine of progress. It inspires generations of scientists to push boundaries, and it plants the seeds of the future in the soil of the present. Each step into the quantum realm is like lighting a lamp in the depths of the cosmos, illuminating the essence of reality. We begin to see that reality may not be as simple as it looks, and existence may just be a fleeting crystallization within a cloud of probabilities. Quantum mechanics challenges not only our knowledge but our understanding of self, time, and destiny. One thing is certain: the journey of quantum mechanics has only just begun. In the coming decades, as researchers push further and develop stronger technologies, we will face wave after wave of astonishing discoveries. From unlocking the origins of the universe, to building machines beyond today's computational limits, to perhaps uncovering the roots of consciousness itself, quantum mechanics still holds countless mysteries. This is a journey into nature, existence, and the limits of human wisdom. The door to the future is far from closed. Quantum mechanics has completely changed our worldview, from determinism to probability, from static reality to observation-dependent existence. It has reshaped the very definition of what is real. From basic research to practical applications, from technological innovation to philosophical reflection, quantum mechanics continues to inspire humanity forward. And the discoveries of tomorrow may far exceed anything we can imagine today.